even though it's two-dimensional. I'm really looking forward to this. But before I say anything else, I would like you to know that everything I say today is a report on joint work with Ilya Chevyrev and Harald Oberhauser, who are both at Oxford, and they were my sort of gateway drug into this crazy world of path signatures. So I would like you to know that I'm breaking many rules giving this talk. So the first rule that everyone says you should follow is have a well-defined outline for what you're going to subject your listeners to, and my outline will have no words. But I do promise you a journey from the world of topology, which is where I spend most of my time, to dynamical systems, to machine learning and data analysis, and then back to topology, but at a very different point from where we started. What this means is that the beginning of this talk is not going to be gentle. It's okay if you don't understand what's happening in the first few slides. Everything will become better instead of you getting progressively lost towards the end of the talk. Hopefully you will wake up more and more towards the end of the talk, which I think is a better way to end. So take a deep breath. And let's begin with some hardcore algebraic topology, which is the study of loop spaces. Again, it's okay if you've never seen a loop space in your life. The definition is that it's the space of all maps. So you take a manifold or a topological space X, whatever you like. It could be Rn, it could be a torus like I've drawn here. It could be a circle, it could be whatever. And you want to study the space of continuous maps from the circle, which I'm calling S1, into X. And there's a bit of detail about what it means for two such maps to be near each other, the compact open topology, if you want to look this up. But so there are two examples. So each of those curves that you see on the torus are a single point in the loop space of the torus. And because it's a function space, some bad things happen. So in general, the loop space will not be finite dimensional, even if X itself, like here, is two-dimensional, but the loop space is hideously infinite dimensional. The second thing, which is exciting to topologists, but you may not care so much about, is that it's a homotopic adjoint to suspension. Now, what that means is, first, let me describe what a suspension is. So the picture that has just appeared on the right, maybe you can see by mouse, that picture is a suspension of the Y shape in the middle. And how you get the suspension is you add a point at the top, which is right over here. You add a point to the bottom, which is right over here. And then you drop curtains from the top to the bottom, cutting across your space Y. So that's a suspension of the Y-shaped figure. And what homotopic adjoint means roughly is that if you have two spaces X and Y, then roughly homotopy classes of maps from Y to the loop space of X are correspond bijectively with homotopy classes of maps from the suspension of Y to X. This may not be in any way interesting to you, but this property gives loop spaces incredibly useful, basically superpowers. So one of the things that's really nice about a loop space is that the homotopy groups, which is, homotopy classes of maps from spheres, so pi I is homotopy classes of maps from I spheres into the loop space, are the same as the I+1 homotopy groups of X. So if you want to study the fundamental group of X, you just have to count the number of connected components of the loop space of X. And there's a lovely product structure where if you choose a base point and all your loops start at that base point, then you can do one loop and then you can do another loop. And that gives you yet another, combined mega loop. So there's a nice product structure. And this is really where you begin studying spectra and stable homotopy theory. But again, I do not want to do that. I want to talk about a much simpler thing, which we also don't know how to compute, which is the cohomology groups of the loop space. Again, I know this is not the right audience to discuss cohomology, and I really won't. But I do want to say that computing the cohomology of loop spaces is incredibly difficult, even for very simple choices of x. The reason for this is what I already said. I mean, even if x is nice, the loop space is hideously infinite dimensional, so there's no nice way to chop it up into pieces, finitely many pieces, that you might understand. So one angle of attack is to try and study if you have a smooth structure on X, which means you have access to differential forms, then you might try and attack the loop space cohomology by looking at differential forms on X. So, well, what does that mean? The space of differential forms is these formal combinations of wedges. So if you have Rn, so the local coordinates are x1 through xn, then the basis of the ith differential forms is dx j1 wedge dx j2 wedge dx ji as the j's increase. So this is just a formal graded algebra, graded by this I. And the d takes you up one step. Here it is. It's called the exterior derivative. You might remember it from multivariable calculus or something. And so this is the derivative of an I form. It gives you an I plus 1 form. Okay. And the idea where I think a lot of the signature theory originated goes back to Kurosai Chen from the 50s, which is that even though there's no nice way to get a handle on this loop space, we can find some part of its cohomology, at least its de Rham cohomology, by looking at forms on X and sort of pumping them, pushing them forward to the loop space. And this is the beginning of the theory of iterated integrals way back in the 50s. So here's a recipe for building an iterated integral. You take a bunch of forms, maybe all of different dimensions, different gradings in the de Rham complex that we saw on the previous slide. So omega 1 through omega k, and you produce out of them a single form on the loop space. So what's going in is k different forms on X, and what's coming out is one single form on the loop space of X. And the degree of the form that comes out depends on the degrees of the forms that went in by this formula. So you add up the degrees of the individual forms. If there are k of them, then you subtract k. Now, in general, this is going to be a complicated object, of course, because I1 plus blah, 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 ik minus k could be a large number. But there's a miracle that happens when all of these things that you fed in are one forms, because you add up k, then you subtract k, so you get a zero form. And a zero form is nice. It's just a function of the loop space. And you can evaluate it at any point in the loop space, which looks like a map from 0, 1 to x, so that gamma of 0 equals gamma 1. And in local coordinates, it looks like this. This should be familiar to people who have been playing around with path signatures. This is exactly a signature of the path gamma. It's a term in the signature of the path gamma. So the image of this integral operator, as defined above, is a differential graded subalgebra. So which means it doesn't necessarily get all the cohomology of the loop space, but it gives you a huge fraction of it. So this was the idea. And to be perfectly honest, topologists seem to have forgotten much about it. This is no longer how people think about loop spaces or their cohomology in my neck of the woods. And the reason for that is the whole assumption of a smooth structure. You might want to compute loop spaces of things that do not look like smooth manifolds. And then all of this sort of becomes harder to do. So other techniques came around. But there's a beautiful property that these iterated integrals satisfy, which is called the shuffle product identity. And it looks something like this. A permutation is a KL shuffle if the following property holds. And you can either read those two lines, which are complicated, or you can look at the picture. So what's on the left is a stack of K cards. What's on the right is a stack of L cards, and you do the riffle, which means that you're allowed to rearrange them between the K and L any way you like, but the ordering on the K stack and the ordering on the L stack has to be individually preserved. So here's the theorem due to Chen. If you take K plus L forms and you compute the iterated integral of the first k and the iterated integral of the last L, then you will get a sum over all possible shuffles of, of all KL shuffles of the iterated integral of the k plus L terms. Right. What this means is on the left side, there is a nonlinear operation. You're wedging things together. On the right-hand side, there's a linear operation. So linear combinations of these higher terms are nonlinear combinations of the lower terms, which will be an extremely useful property later on. But OK, so this is the story of iterated integrals in topology. This is the birth. Again, this looks very different from maybe what you have been playing around with if you actually play around with path signatures. And the reason for that is that the spaces are extremely bizarre. These paths are taking values in an X, and the X can be a terribly complicated space. Anyway, and the functions are sort of nice, right? We're doing all of this with differential forms, which means all the functions that show up here are smooth functions because you need to take derivatives. OK, so here begins the next stage of the talk. We're going to transition from topology to dynamics. We'll do it through the theory of Picard iteration. It's just a story of how one can solve a given ODE. So there's an iteration scheme where the I plus 1th term is a constant plus the integral from 0 to t of the function evaluated at the ith term. OK, so this is Picard iteration. Hopefully you've seen it before, but if you haven't, let me give you an example for the simplest case. So dx dt equals x. I know we can all solve this equation, but I'm trying to show you the iterates. So let's start at the constant 1. So that's our first initial condition for the iteration. And so by the formula above, the first term is going to be x1 of t, which is 1 plus the integral of the constant, which is 1 plus t. Then you have a quadratic term, which looks like that, 1 plus t squared, and so on, while you discover the power series formula for the exponential function. So this is baby Picard iteration. And where the magic starts is when you have differential equations controlled by paths. So they have the form dyt is f of yt dx of t, and f is some function taking values in matrices. A path solves this equation, of course, if you integrate on the right side and you get an equality. So there are many applications where f is a beautiful, nice linear map, but the paths have very, very small levels of regularity, so that you can't really take any derivatives. So one interesting space of paths is the space of bounded variation paths, where over every partition, when you look at the successive difference and add up the norms of those, you get something finite. And Terry and company used Picard iteration to solve control differential equations for instance, when x is in the space of bounded variation paths. And so here is their lovely solution. You first replace this map F with a different map G, which takes values in the n by n matrices using the this formula. It looks complicated, but you're moving. Well, topologists like to call this the Hom-tensor adjunction, but I don't want to inflict that on you, so I've given you sort of precise formula on the slides there. So again, let's start Picard iteration and see what happens. The first term is constant. The 0th term is constant, rather. And now the first term is c plus the integral of the previous one, which gives you just the integral from 0 to t of dg x of s. And now when you do the second iteration, you start to see things that were very, very similar to the old iterated integral formula. In fact, you're getting exactly the same iterated integrals, and so on. And each of these terms have the formula, have this form, 0 less than t1 less than tk all the way less than t, and then the product of dg xt1 all the way down to xtk. And I sort of want to emphasize between, I mean, these integrals look very similar, but there's a huge shift in philosophy between what was happening with in the pink slides with all the topology and what's happening in the blue slides with all the dynamics. Roughly, the spaces that we're working on have become stupider, in the sense that instead of working with a general X manifold or whatever with the loop spaces, we're now looking at Rn. On the other hand, the functions that are involved have become much, much more interesting. They're no longer simple, smooth functions. They're just barely, you know, these bounded variation paths. So that's the big difference between the two. But the formulas, the iterated integrals, these look the same. So I guess I'm preaching to the choir, but I will tell you what the definition is anyway. The path signature is what you get when you take in a path and you spit out this object where which is graded, and in the 0th level of the grading, you just have 1. The first level of the grading, you have all the increments. So you go from 0 to 1 of the derivative. And then on the second level, you have these twice iterated things. So this is over the domain 0 less than t less than 1, and then so on and so forth. So the reason the strips are getting bigger is because there's more and more level 3. There's more level 3 terms than level 2 terms, more level 2 terms than the level 1 term, and so on. And of course, the signature is this element that lives in the tensor algebra. So that's the product of all of these terms. And M is indicating the level of the signature. And if you're dealing with finite amounts of patience and computer memory, then it's customary to just truncate this whole thing instead of going all the way out to infinity at some high fixed M. And of course, the mth level has n to the m components, which is why the strips are getting fatter. And it might be helpful to go over some of the lovely properties that the signature map has. So it's this is the part that I'm sure a lot of you understand a lot better than I do. But I want to say that the components in each level of the signature are just chance iterated integral functions, which where each omega I is, each one form that you've chosen is dx with respect to one of the coordinate variables. And of course, the kernel of this map is interesting. If two paths have the same signature, then they differ by what's called a tree-like reparameterization. It is basically, not basically, it is exactly a homomorphism from the space of paths with the concatenation operator to the tensor algebra with, of course, tensor products on the right. And every multi-index corresponds to a term in level k of the signature, where k is the number of terms in your multi-index. And you have the same shuffle product identity, where if you multiply the signature with respect to two different indices, then you get a sum of the signature with respect to shuffles of the union of those two indices, which I think are all properties you know. And it is because of these properties that it is such a wonderful tool for statistical inference and machine learning, which is the third part of our of the journey. And so it maps this bounded variation space, space of bounded variation paths, into a tensor algebra. And you may not suspect that this does anything useful, but it does. So one of the great things it can do is find all sorts of correlations between paths. Again, people who are listening have a much better sense of what the many success stories are of using signatures for sort of time series and handwriting recognition and Chinese characters and all the stuff that that I've forgotten. What I would like to use them for, what Harald and Ilya and I wanted to use them for, was for data coming out of my field, which is topological data analysis. And for this, we needed some other glorious properties of the signature. So if you take the space of bounded variation paths of a vector space and you quotient it out by the signature's kernel, which is the tree-like equivalence, and take a compact subset, then the signature map is universal, which means Each continuous map can be uniformly well approximated by a linear functional, just applied to the signature. It's characteristic, which means the map that sends a probability measure to its expectation is injective. And of course, it's kernelizable, which means you can actually compute things. Okay, so what sort of things are we did I want to use them for? Well, my field is topological data analysis, and it is the study of finite point clouds, finite metric spaces using cohomology and homology, which I've promised I will not go into detail about. So this slide is just a sort of cartoon introduction to the entire field, and I apologize to all my TDA colleagues for reducing their life's work to this slide. So you start with a finite metric space. There it is. I don't know how many points it has. 1, 2, 3, 4, 5, 6, 9 points, I think. And then you pass to the a sequence of spaces that are getting larger and larger, that are indexed by a single real number, which I think I'm going to call epsilon. So this is x0, which is the same as x. You just have the same copy. And this is x at some intermediate epsilon. And what we've done to get from x to this intermediate space is anytime 2 points have distance epsilon, I connect them with an edge. Every time 3 points have, can be contained in a ball of radius epsilon, I connect them with a triangle. And you can do this at bigger and bigger epsilons and get bigger and bigger spaces. So what we've built here is really called a filtered simplicial complex. And you can go all the way out. When you go all the way out, you just get completely everything connected to everything else blob. And by examining sort of adjacency operators, the way you would for graphs, right? So if you had a graph, you could look at the adjacency operator from the vector space of edges to the vector space of vertices. Here you also have triangles, so you have another adjacency operator going from the space of triangles to the space of edges, and from the tetrahedra to the triangle. So there's a huge family of adjacency operators, and you can look at the kernels and images of that to produce what's called the homology groups. So this is going to be a 1-parameter family of vector spaces with the coefficients in some field. That's what the F is over here. And these are capturing sort of interesting properties of the shape that gets generated as you change epsilon. So the two that are most familiar are H0. So H0 is just counting the number of pieces you have. So H0 for our original X is going to be 9-dimensional vector space over the field F. So if F was R, then you just get Rn as H0 at epsilon equals 0. As epsilon becomes bigger, you say you just have one connected component because you've thrown in edges and triangles and so on, then H0 will just be 1. Similarly, H1, the 1-dimensional homology group, is counting the number of loops. So in the final epsilon that I've drawn here, there's one big loop here and one tiny loop here. So H0 would have, I apologize, H1 would have dimension 2, 1 per such loop that you find. Okay, anyway, whatever it is, you get a sequence of vector spaces. Then there's a bit of representation theory, which goes from this sequence of vector spaces in each dimension, D, to what's called the barcode of X. And I would like you to think of each of these bars as a birth and a death event. So a bar goes from, let's say, 5 to 7. If at epsilon equals 5, a hole was formed, and at epsilon equals 7, some triangles were thrown in that filled up that hole. So it's just a summary of births and deaths that occur in the sequences of vector spaces. So you get one of these in each dimension. And then you would like, ideally, to feed these into some neural network and learn, learn to classify different X's depending on the problem. So if you had X's coming from 2 different processes, maybe you'd like to classify. So X could be points drawn from distribution 1, and X prime could be points drawn from distribution 2. So you get lots of chances to sample X, lots of chances to sample X prime. And the hope is that when you do this whole process, you go through this nonlinear process, you somehow are able to distinguish the things drawn from the first distribution and the point samples drawn from the second distribution. So that's the hope. Before I tell you where the path signatures come into this entire story, the red arrow is where they will come in, of course. We're going to use path signatures as a way to feed barcodes into neural networks. That's the whole idea of what we wanted to do. But let me point out that the reason this sort of thing is not patently ridiculous to do with data is that there's a lovely stability theorem. So here's our metric space that we started with. And let's say this was the barcode in some dimension, D. Let's say there was some noise in how you got these points, which means you perturb all these points. That's the level of error. So the gray balls that I've drawn around these points. So the real point could be anywhere in that ball away from the sample point. So what that means is if you perturb this original point so that each original point cloud so that each point gets sent somewhere in the gray ball, then the changes to the final output, the persistence diagram or the barcode over here, are just at the endpoints of the bar. So that very long bar that you're seeing can only get a little bit smaller. That same radius that you perturb the points by, but that tiny bar could disappear entirely. So this is the long bars are somehow telling you about all the spatial features of your data that are invariant to these minor fluctuations. Anyway, so this is a nice stability theorem. And as you might imagine, with the sort of resurgence or maybe let's just say enormous amounts of attention that deep learning has been getting over the last, I want to say, decade now, there's been an enormous amount of activity which is trying to feed these barcodes into neural networks, which really what this requires is a vectorization. And the trouble is that the space of barcodes is extremely nonlinear. So it's a metric space in its own right, but it's very much a nonlinear vector space. Nonlinear metric space. So just sort of listing the endpoints or something to convert, this sequence of intervals to a vector is going to lead to terrible performance. In fact, you can try it. It will be terrible no matter what your application is. So there has been an enormous amount of attention paid to getting vectorizations or feature maps for barcodes. You might think I'm joking, but it started with that paper on something called persistence landscapes. And then it kept going. And if you look at this last list of authors, you will see there's someone from a Department of Mechanical Engineering. And when there's someone from the Department of Mechanical Engineering who thinks that you need a feature map, that you are desperate. And there's so many of these. And these are just 5 or 6 that I've chosen here. But I think in the last year, there have been 3 or 4 others, ways of converting these barcodes or persistence diagrams, as they're also called, into vectors that you can then use for, in a standard neural network. So this is where things were a couple of years ago. And then I had some interesting conversations with Harald and Ilya, and Harald suggested the following pipeline, which is you have a barcode. Let's encode it somehow as a bounded variation path, and then apply the signature. And then you get something in the tensor algebra, and now you have something living in a vector space. So that second map is the signature, and I've been singing praises of it for a long time. So maybe what I should do is give you examples of what the first map can be, this embedding of barcodes into bounded variation paths. So I think there's many interesting ways of doing it. So we chose 3. And these are called persistence path embeddings because they embed persistent homology information into paths. And of course, S is the usual signature map. So the first one I want to show you is called the landscape embedding. And here you start with barcode, and then you take a bar AB, and then you plot it as a point AB in the plane. So here we have 3 bars that have become 3 points, and then you take that picture, and then you rotate it, and then you get these 3 sort of peak functions. You just take the upper envelopes. So this has gone from a barcode with n bars, roughly, to n different paths. And this assignment it respects the stability theorem. So if your bars move by something, then the L infinity distance between the corresponding functions, these tent-like functions called the landscapes, also is the paths are also L infinity related by the same. So and what happens is if you partially integrate these, you take the antiderivatives of these paths, they also inherit the stability property. So that's great, except this is not as computable as we like. So this is, as it inherits all the lovely stability properties of TDA, but getting signatures of these antiderivatives of landscapes, at least a year and a half ago when we were working on the paper, was difficult to do. The reason being, it's no longer piecewise linear. I mean, the landscape itself is piecewise linear, so when you integrate it, you get something piecewise parabolic. And if any of you knows a good way to integrate piecewise parabolic paths, please let me know. I would be very happy to try this out. Okay, the second one is called, it's split into 2. There's a hard one and an easy one. So the harder one is called the Betty embedding. So you take each dimension and each scale t, you let beta sub d of t be the number of bars that contain t in the d-dimensional barcode. And then the assignment of t to b beta dt gives curves in Rm, and m is the largest dimension where you have simplices. So this is not stable, but it's extremely computable, and it contains all the sort of a lot of the interesting information level-wise. So at each t, it gives you all the sort of shape information that you'd like, the number of connected components, the number of holes, etc. And so Betty 0 of t is literally the curve that when you thicken the data set or your metric space by t is counting how many components it has. So that one always declines because it starts with the number of points you have and ends at 1 and monotonically decreases. The other, so Betty 1 is counting the number of loops that you see as you thicken. So that goes up and down, but it's always taking sort of integer values unless you renormalize it. The Euler embedding is even nicer. It's the easiest thing to compute on the planet. This is the alternating sum of the Bettys over the dimension. And there's a consequence of the rank nullity theorem is that instead of computing all these Betty numbers by doing linear algebra, you can just take alternating counts of simplices in the simplicial complex. So the number of, at scale t, you've taken your metric space by t, and you've thrown in triangles, tetrahedra, etc. So chi of t is going to be the number of vertices minus the number of edges plus the number of triangles minus the number of tetrahedra, so on all the way up. So this is, as you're entering your data, you can compute this. This is also, because of, the Betty numbers are not stable, this is also not stable, but it's really nice to compute. And the final one is the envelope embedding. You just lay out your bars, birth and death, in descending order, and then you connect all the deaths and you connect all the births, and you get 2 curves, no matter what the number of bars is. It's always 2 curves. This is called the envelope embedding. And so you get like a birth curve and a death curve out of it. And the point is that the longer, stabler bars appear before the shorter, unstable ones. So if you truncated this at some point, you'd still have all the stable information living on the left. Okay, so this is, I think I've taken you, I promised to start you off with topology, take you to dynamics, take you to machine learning, and then bring you back to a completely different part of topology, which is this TDA instead of loop spaces. But I don't want to end here immediately. I just before ending, I want to show you the sort of payoff So we tried this with three data sets, and off the long list, the laundry list of other featureization maps or other vectorization maps for barcodes, we compared with the top two. And here are the results. So there are three data sets: textures, orbits, and shapes that form the columns of this matrix. And above the horizontal line, the KSW and the VPI are, other people's state-of-the-art vectorizations of barcodes, and below are the three of ours. And the Ks are the kernelized versions, and the Phs are the unkernelized versions. And I want you to see what happens. So we didn't compute the landscape ones because, like I said, we were not able to compute signatures of piecewise parabolic paths. But the others, the Euler, the Betty, and the envelope, we computed all of them. And so the winners here, for at least textures and orbits, we did much better than the existing state-of-the-art. And so for orbits, as you can see, we lost. There's a 99.86. I mean, we did pretty well. There's 98.8 for the Euler one, but we lost. And this was very depressing until I found out what had happened. So Ilya, who was working on this at the time, looked at what had actually been done in the paper where we were getting, and their actual results there were 83 something, but he implemented their method better than they did, and then it beat us. So I don't feel like this is a loss. I just feel like this is Ilya being as charitable to the competition as possible. Anyway, the paper has appeared in the Transactions of Pattern Analysis and Machine Intelligence. You can find it online if you have an IEEE login. Otherwise, you can find it on my website. And if you would like, I understand that not all of this would have made sense to you. Hopefully, some part of it did. And if you want references for any of this, these are my favorite sources right now. For the topology part at the bottom, Kurosai's Chen original paper is difficult to read, but contains everything. Much more modern write-up of the interesting parts of it is this paper by Chad Giusti and Derek Lee, Iterated Integrals and Population Time Series Analysis. If you like the dynamics section, then the St. Flower notes of Terry and Company, or the course of rough paths by Fritz and Heirer. And if you love the machine learning part, I can not recommend highly enough Ilya and Andrei's survey paper called The Signature Method in Machine Learning. And with that, I will say thank you and take any questions you have.
Vidit, that was